Hello everyone, and welcome to this video titled Function Rules Based on Graphs. In this video, I'm going to be going through several examples taken from the Adaptive Practice at a website called ck12.org, and I'm in their Algebra 1 text. Okay, so here we are at ck12.org in the adaptive practice called Function Rules Based on Graphs, and I'm in their Algebra 1 text, as I mentioned. And I'm only going to be doing 5 out of the 10 problems here in the adaptive practice. Of course, you can go in yourself and complete all 10 and even work further after that for further practice. And of course, read the text and do all the normal things you would do to, get better at a certain material. As I work through this, I would recommend when I start a new example that you pause the video and try to work things out yourself before watching me do them. All right. So in this first example, we're asked, which of the following rules represents the graph below? So we're given a picture here, the XY coordinate plane, and a red line, right, a red linear graph. And we're asked to express the equation, for this linear function, this linear graph, and we're given several options. All right. Well, we could go through each of the options one by one. What I'm going to do instead is take a look at this graph and point out, some ordered pairs, some obvious points that are on the graph in a little chart, and see if, any of these rules fit that chart. So I'm going to make a little chart here with x values and their corresponding y values. I noticed that the origin was on the graph, right? The point 0 for x, 0 for y, right here, where my cursor's floating around. And another nice point that's pretty obvious is when x is -2, y is 1. So I'll write that down. So when x is -2, y is 1. And I'll put one more up for good measure. Being that it is a straight line, we really only need 2 points, right? You only need 2 points or 2 ordered pairs to determine where a line is going, but let's just throw one more up here. Another point that is, one of these grid corners is this point here where my cursor is floating around. When x is -4, y is +2. So I'll write that down in my chart. So when x is -4, y is +2. All right, so based on these three, it looks like the y coordinate of every single point is -1/2 the x coordinate. So -1/2, you can write 1/2 or -0.5 times the x coordinate. And you can test this out, right? When x is 0, 0 times anything is 0. -2 times -1/2 would be +1. -4 times -1/2 would be +2, right? So this right here looks like the proper rule for this particular linear graph we are given. And of course, you could go through the other three options and see why those wouldn't be working. If y was +half x, well then -2 for x would map to, -1 y, not positive 1. And if y were equal to x itself, then -1 should map to -1, and -2 should map to -2, and that's not happening. And same thing for y equals, -x. -1 would map to +1. -2 would map to +2. And again, that is not happening in this particular picture. So the only one of these that makes any sense, the only one that fits, is y equals -1/2 x. Check it out. Beautiful. All right, so moving on. All right, so once again, we have a linear function, right? A linear graph. And, pull up my scratch pad. And you know what? Let me point out what every single, if you have a graph of a line, or if you have a linear graph, a linear function, every single one of these graphs will look like this. Y equals, or, could look like this. They don't always look like this, but they could look like this, every single linear graph. Y equals m times x plus b, right? Where this number m, right, this number attached to the x is referred to as the slope of the line, but we'll get into slope later. All right, we're not, this isn't a lesson on slope. Just wanted to point out the word. We will see more about slope of a line at a later time, I am sure, in a future video. And, when x is 0, y is b, right? If the value of x were 0 in an equation like this, m times 0 is 0. 0 plus b would be b. So the y-coordinate would be b. And, this would be called the y-intercept. Now, we've seen in a previous video from earlier in this Algebra 1, Chapter 1 of the ck12.org book, we've seen the definitions of, y-intercepts and x-intercepts. All right, so again, I'm going to try to write the equation like this, and notice all the options are like this. Y equals, some number times x, and then maybe plus some other number after it. All right, so let's see. Like in the previous example, I'm going to write down a little chart, with some ordered pairs, and I'll definitely point out the y-intercept, right? As I pointed out the y-intercept here. But let's make this little table for our particular example. When x is 0, y is 1. That's your y-intercept. That's clearly the point here. I'm also seeing that when x is 1, y is 0, right? That would be the x-intercept. And when x is -1, y is 2, and when x is -2, y is 3. I'll put those points on my chart. All right, so when x is 1, y is 0. When x is -1, y is 2. When x is -2, y is 3. All right, and then from this, if I'm trying to write an equation that looks like this, y equals some number times x plus some other number, it looks like y equals, the opposite of x plus 1. Right, and again, this takes a little practice, takes a little getting used to, but I'm seeing this pattern here, right? The opposite of 0 plus 1 is 1. -1 plus 1 is 0. +1 plus 1 is 2, positive 2 plus 1 is 3. Right? Every single y value is just the opposite of the x value plus 1. Right? And once again, it is a multiple choice question. So you could have also run through, the other three choices and seen that they do not fit the graph given to us, the graph shown to us. The only one that fits, the only one that actually has the correct ordered pairs would be y equals negative x plus 1. Check it out. Wonderful. Okay. Now we're given a graph that is definitely not a line, all right, not a linear graph. This graph here is what they call a parabola. And we've seen parabolas in previous videos from this Algebra 1 text. A parabola has a highest power of x squared, y equals something involving x squared. Now, two of these are possibilities, right? So again, because we're not really diving that deep into this just yet, this is still Chapter 1's introduction to functions in this Algebra 1 text. We'll go into more detail in a later video on writing equations of what are called quadratic functions. But of these, the only ones that would be parabolas have x squared as the highest powered term are b and c. Now a has a square root function, square root of 2x. And then b is what they would call a cubic function, right? Its highest powered term is x to the third power, x cubed. And the graphs of those are not parabolas. Right, so of these, we're looking at B or C. And then looking at the ordered pairs in my graph here, I'm seeing that when x is 1, y is 0, the x-intercept 1, 0 is on the graph. And so is, negative 4, 0. Those are the x-intercepts, 1, 0, negative 4, 0. And it looks like C is the correct choice there, right? Because in B, when x is 1, you'd have 1/3 plus 1/9 as the output. The y coordinate would be 1/3 plus 1/9, which would be 4/9 if you were to put those together, get a common denominator and put those together. That's not 0. But in C, when x is 1, you get, 0 times 5, which is 0 as an output. And when x is negative 4, you'd get negative 5 times 0, right? Negative 4 plus 4 is the second factor, and that's also 0. So the only one of these that ends up having a, x squared as the highest powered term, right? If you were to multiply these out, you get x squared plus 3x minus 4, and has the x-intercepts 1, 0 and negative 4, 0. This choice C is the only one. Okay, check it out. And again, with practice, right, with enough experience, enough practice, going through enough examples, you'll hopefully be able to recognize when you look at a function, like a square root function, a quadratic function, right, a square function, or a cubic function, or a linear function, hopefully you'll be able to recognize with enough practice, with enough experience, what those graphs would look like. So next example. Right, now this time, we're given a set of ordered pairs that belong to some function. Right? Find the equation that relates the x values to the y values in each function. So 2 to 9, 4 to 19, 6 to 29, 8 to 39. And I'm looking through the multiple choice options here, every single one of these starts with y equals 5x, y equals 5x, y equals 5x, 5x. So I'm going to take 5 times each of these x coordinates, and then we'll just need to figure out what needs to be added to give me the correct y coordinate. Well, for the first pair, through 9, 5 times 2 is 10, and then I'd have to subtract 1 to get 9. 5 times 4 is 20, minus 1 would be 19. 5 times 6 is 30, minus 1 would be 29. And 5 times 8 is 40, minus 1 would be 39. So it looks like B, right? Y equals 5x minus 1, right? Every y coordinate in these ordered pairs was just 5 times the x coordinate minus 1. Check it out. It's simple enough, just like the linear equations in the first two examples. And that's all it looks like we're really doing here is, given some ordered pairs, given ordered, pairs in a picture, pairs in a set like this, can we, suss out what the correct rule would be? Right? Not a whole lot of work going on here yet. All right, and then my final example, right, same as example 3, where it's not a linear function. It's also not a parabola, and it's not a square root function. In fact, let me write out just some general shapes for some basic functions. All right, so your linear functions, all right, those graphs will be some sort of straight line. And this is y equals, as I mentioned earlier, y equals mx plus b, y equals x to the first power. Then you have your what are called quadratic or square functions. These are parabolas, right? Now I'll just put the most basic one up, y equals x squared, but it's anything where x squared is the highest power. You'll have a parabola shape that's either opening up like I drew here, or opening down. And in fact, I'll just put the most basic version of all of these. Cubic function looks something like this. You have y equals x to the third power. And, anything where you have these powers, x to the first, x to the second, x to the third, like this, these are called polynomials, polynomial functions. Now we also could see a square root function. Right, the square root function is like the top half of a parabola opening to the right. Y equals the square root of x. Cube root. Cube root is like a cubic, but turned sideways. Y equals, the cube root of x. And, if I were to continue this, you'd have other roots, right? So fourth root, fifth root, and so on. So those are some basic polynomials, basic roots. Other basic functions, let me clear this. You have your basic reciprocal function, where y equals the reciprocal of x, right? Remember, the reciprocal is just flip it over, x becomes 1 over x, x over 1 becomes 1 over x. So in that case, the graph looks something like this. You can't have x be 0, right? You'll have what's called a vertical asymptote. And same thing, y can't be 0 either. You'll have what's called a horizontal asymptote. The graph will get closer to the x-axis, closer to the y-axis without actually touching it. And then you have what they're trying to get at in this example here. These are called exponential functions. These look like this, y equals, and then it's some number to the x power. Now, if that number is bigger than 1, then the graph will look like this. Be an increasing function, and then really get it grows real fast, right? Y equals 2 to the x, 3 to the x, 4 to the x. As x increases, right, the power increases, it gets very large very quickly as you move from left to right. And it's never negative. You actually have a what's called a horizontal asymptote at the x-axis. The graph is always above that. And if you plug in negative numbers, you get really small values, right? Some number 2 to the negative 1 is actually 1 over 2. 3 to the negative 1 is actually 1 over 3. Negative powers are just reciprocals of the positive powers. So you get really tiny positive numbers. And if the base is less than 1, if the base is between 0 and 1, we get a decreasing function. It's almost like when the base is larger than 1, reflected across the y-axis, right? So it'll be decreasing. Yeah. There's your generic shape for your basic exponential functions. All right. And so what I've got up here in this example is like one of those where you see the graph never actually touches the x-axis over here on the left side, and then shoots up, increases very rapidly. So this is one of those exponential functions where the base is bigger than 1. All right. So like this. It's like this. And, you got your square root type function here. Choice B is a quadratic function with a negative number in front of the x squared. Choice D is also quadratic. If you were to multiply x minus 4 by x minus 4 again, you'd have x squared minus 8x plus 16, another quadratic expression. So the only one of these that will behave this way is like this exponential function with a base bigger than 1, right? Base bigger than 1 is C, 3.1. Y equals 3.1, or f of x equals 3.1 to the x power. Check it out, right? Great. So yeah, so like I said earlier, with experience, you'll come across all those different kinds of functions and even more. That list of functions I put up there with y equals x, x squared, x cubed, square root of x, cube root of x, 1 over x, b to the x where b is bigger than 1, b to the x where b is less than 1, between 0 and 1. Those aren't all the kinds of functions you're going to come across if you continue on in math, through pre-calculus and calculus. There are other functions called logarithmic functions. There are trigonometric functions, inverse trigonometric functions, and more. Right. I can't list all the kinds of functions you're going to come across in this one little video. And again, if you're reading the texts, practicing problems, hopefully with enough of that, you'll understand, have a rough idea as to what each of these kinds of functions that you come across should look like. And I've said that several times now throughout this video here and in previous videos. All right. So again, hopefully watching me go through these helps you out when you're working on this on your own. I recommend getting through all 10 of these if you're working on it at home, and maybe even practicing even further after that. So you really get hammer in your head, get it down, all the different kinds of shapes that you might see, at least in this beginning part of the Algebra 1 text here at ck12.org. And of course, that list of functions will be built upon in later videos and later chapters. Okay, have fun with all that. Thank you very much for watching.